Social stuff. So this is the AQM working group meeting. If you're still here from the last meeting, please leave the room. We have a pretty tight schedule, so I would like to start right away. We have already a Java scribe. We have a note taker. Thank you, David. Thank you, Corinna. Or the other way around. So you're here in an IETF meeting, so the note well applies. All of you knows what this is. So I'm skipping over it quite quickly. So current agenda. So I know that I've got some feedback. Anybody disagree with this agenda? Going once, going twice, and sold. So we go with the agenda as it is published. First, I'll have a short summary on the status of the working group. Then we will have 3 quick updates on the status of the 3 drafts of the evaluation guidelines, the ECN benefits, and fair queuing CODL. After that, we have a presentation by Bob Briscoe, which came, I believe, out of the PI review as part of it. Then we have a live demo with dual-coupled AQM by Köhn. And after that, we'll have Wolfram presenting his GSP AQM again, which recently received the Best Paper Award at SICOM, as far as I've understood. And if time permits, Bob will go further into his review of the PI draft. I don't think that we have anything for the last item actually. Major milestones that we've achieved. We've passed our first RFC. So RFC 7567 is the long discussed AQM recommendations. Thank you, Gori. Thank you, Fred. The other, yeah, thank you. Other working group items that we are basically working on. So we have actually 2 drafts that are currently in working group last call. We have ECN benefits. This has been in the working group last call already, with Gori receiving quite some feedback during that round. I believe, but he can comment on this, that all the feedback was addressed. So if nothing else happens, we will close that working group last call at the end of the week or early next week and go for publication. And we also have fair queuing implementation guidelines in working group last call, but I believe that's depending on some of the other drafts. We have upcoming working group last calls for the evaluation guidelines. And of course CODL. On CODL we have a dependency with fair queuing CODL, where we also get an update today. And we have seen quite a lot of feedback for PI, but we have not yet seen that much of these feedback has been discussed by the authors. Okay, with this, I would like to have Nicholas up here. Yeah, please. Just a moment. Where is it?
Okay. Okay, so hello everyone. This is just a very quick update on what has been done on the characterization guidelines since the last IETF. Basically, I just summarize here with the different steps. From the second version to the third version, we have included GORI's comments, and basically we have a more accurate terminology for all the must, may, should that was not really good before. We have added a scenario on when you have AQMs one after the other, and we also have added that it was not clear in the draft what test was actually needed, what was requirement for each test. So we have added a table that summarizes all the tests and the requirement for each test. Then we have assessed Jim's comments. Basically, the main here I just summarize the main 2 points that were erased. Is that basically Jim wanted us to have running code, but that went somehow in conflicts with the fact that we want the guidelines to not to be very dependent on the platform used to test the algorithms. So that can hardly be possible. And also we did not speak much about packet scheduling. We have extended this section a little bit, but the problem is that packet scheduling is something that was not in the, but the memo at the beginning just refers to AQM, that is dropping or marking schemes, and not really to scheduling in particular. So we believe that these guidelines may be completed with another document that access the specific case of scheduling and all the scenarios that goes with it, like flow starvation or all these kind of things. And if such document appears to be written someday, this document will obviously consider all the tests that we have set up, but just add some more scenarios. And then from the fourth version to the next version, the version that we have today, we just had a couple of English needs, and also we have updated the way to present the metrics with ellipses like it is done in case Winston style. So in that sense, I think that we have included most of the comments that we have received. Try to make consensus on them. So I believe that, I mean, according with the chair, that we believe that the document may be ready for a working group last call. So this is it.
So any comments on the current status of the document, and if you're ready for working group last call? Gori?
Gori first. I think this document is a sort of document which will never be perfect. I've read it. I think it's really valuable. I think we should just last call it.
Okay, good. I mean, this was pretty short. Thank you very much. And the next speaker, please. Which incidentally is Gori.
My first time in a pink square at this IETF. Hi, I'm Gori Ferris. My co-author is Michael Veltzel. And this is about the benefits of using ECN, or the ECN manifesto as we have called it. This document has just been quickly revved in the last very short period to include a few typos and things, but it basically was a result of a long set of discussions on the mailing list about the detailed wording of various sections. You can see on the list many little topics which were discussed in detail to try and get the right wording out. I believe that everybody who commented is now happy. If not, now is your chance, because on the next slide, we think we're done.
And again, I want to point out that this document is already in working group last call, the second time. And ideally, we want to close this out somewhere during next week.
So this is your chance to reread this document, and if you have anything more to say, please say so. Thank you.
Yes, hello. Moving on, same thing, next draft, FQCODL. That was adopted in Hawaii, though that seemed to have slipped the agenda for today, but it is a working group draft. We've had a couple of review rounds on it. The last one was submitted a couple of weeks ago. Next slide. So changes since the last time you heard about it, which was in Honolulu. We've referenced the CODL draft instead of reiterating how the CODL algorithm works. We've put in a couple of new sections about alternative classification schemes, limitations, and some further work. There's a new parameter in the upcoming 4.2 of Linux, which allows CODL to have a separate threshold for CE marking, which we've included now, and then there's some minor edits and readability stuff done in the last couple of revisions. And well, as before, we think the algorithm describes, or the document now describes the algorithm as it exists today. It's had a couple of revisions. People have read it, but if anyone else wants to comment, of course, more reviews is always nice, but otherwise, it's informative. The algorithm's there. Should we just ship it and get it done?
Okay, so obviously this has a dependency on CODL, where the author is coming to the mic.
Well, editor, mea culpa, we are not ready to ship that quite yet, but all going well by the next IETF meeting, and ideally within a few weeks we should be. So I think deciding to ship this, other than that it will take a normative reference on another document that will delay it in the queue, I don't see a problem.
Yeah. So Bob?
Just to say that I've read it and just haven't typed up my review, so I'm promising you a review shortly. It's a good document. You've made a lot of effort to make it understandable. There were still some bits I felt were ambiguous, but
yeah, no, I was hoping you would go on the microphone and commit to that.
Okay, good. Sounds good.
Just
so, Bob, since you're standing. Yes.
all right. Richard said this was from me having reviewed Pi. It was actually partly that and partly from the work Koen is going to present next. Koen de Schepper is going to present next, and all the experiments we were doing on that. And you can think of this as either a comment on the original goals of CODL and Pi, or you can think of it as a preparation for why we're some of the motivation for why we designed the dual queue coupled algorithm that Koen is going to talk about next. Also, I should point out, first off, any AQM will do. This is really about when I was working in BT, it was which one is best. You know, what should we avoid if we want to make sure we simplify things and use this instead of diffserv, say, and have more low latency traffic and not have so many classes and all that sort of thing. So this is more about making sure it's correct at the boundaries of load and things like that, rather than worrying too much about what any AQM will do is the first message. So when we were looking at CODL and Pi, we ran some experiments where we were just loading up with more long-running flows, and we came across very high loss levels, and we sort of get a bit concerned that everyone's been focusing on delay and they've not been looking at loss. And so this little block of graphs here is just for 250-second duration each run, measuring the average loss probability over each second, and the vertical scale of each cell is 5%, 0 to 5%. When we got to 20 flows, we were up at 4.2%. This was FQ Coddle. Pi gave similar results, not quite as bad because it was not giving quite as much delay. So this talk is about what we did to work out why that was happening and what you might want to do as a consequence. And the top level summary is that you cannot get TCP to give you low delay if you want low loss as well and high utilization. TCP is like a balloon. When you squeeze it one way, it will just come out another. And it will either give you higher loss if you want low delay or lower utilization or whatever. And you can't have them all. Right? I guess one more point before I go on to this slide. However, you don't necessarily want to have the sort of loss levels like 4.5% because that gives you more knock-on delay than the queuing delay would have given you. Because, you know, all the timeouts and tail losses and things like that. So this is sort of saying maybe you want to relax those configuration parameters a bit and not quite go to 5 milliseconds. So anyway, next slide. The insight for this came from another algorithm we wrote, and in a way I'm sort of saying that it's a better algorithm. It's certainly simpler. It's at least as good, and we're calling it curvy red. It's sort of like red, except it's curvy. It's just as polynomial, you know, either a quadratic or a cube or a quartic curve. So it's a bit like the red flat and then up a bit and then up a bit further, but it's smooth. Yeah. And the reason why that became interesting to us is because we worked out a really easy way to implement it. If you want a square curve, red is a linear curve where you take, you throw a random number and you check whether the Q is greater than that. We just throw 2 random numbers to get a square, 4 random numbers to get a quartic curve, and so on. But I'll come on to that. And the nice thing about this is that as the load increases, if you double the load, you don't sort of get 2 times more Q because the pressure increases the further you go up the curve. So you don't get more and more delay, but you do get some more delay, but it means that you don't get as much loss as you did before, and you'll see that in the next slide. So it's essentially drop probability equals D means delay, queuing delay to the power of some U parameter. U is curviness, with the second letter reminding you curviness. And the bottom, capital D, capitals tend to be, I use them for constants, is the just the point at which it hits the 100%, and that gives you the slope. So if you move that, you'll get a sharper slope. And there's just a picture there of 2 curves, one square, 1 to the 4th, with different values of D. So they both cross at about 20 millisecond or 2%. Right? And this is the implementation. It's quite short. It's 1 line, 2 lines if you include the drop. It's just bit shift the Q in time. If it's greater than the max of 2 random values, drop the packet. And the previous line in the code is smooth the Q. So the value of DQ there is actually EWMA'd like red does. So it's pretty simple. If you want to do the quartic curve instead of, you know, or have a general way of configuring this curviness value rather than having if it's this line of code with 2 random errors, just do a while loop on the number of random numbers you want to pick. But the nice thing about that is that you can generate the random numbers and the maximum of 2 of them in pairs into a buffer off out of band, or if you're doing it in hardware into some bit of memory, and then just pull them out of there like they're brand in Linux. So you don't have to do those random numbers at the point you're trying to dequeue the packet. Next. So then, this slide I want to dwell on a bit, and I'm sort of want to wave my arms at it, so I might have to get out of the pink box. Or I suppose I could use one of those laser pointers which I have in my bag. We'll see how we go. So essentially what this says is, and let me explain the graph first. Essentially you can think of the horizontal axis as more flows. It's normalized load, which means I've done it so that it's applicable whether you have a large amount of capacity. So 10 times as much capacity, you would be able to have 10 times as many flows. Okay, thank you. Right, and I guess that's, yep, okay. So normalized load proportional to the number of flows divided by the capacity, right? And so you can think of that as the pressure that's being put on the link, the more flows you put into it. And then if you think of at any point, the vertical line for that normalized load gives you, for a particular value of curviness, it will give you, if you take curviness 1, it will give you dq on this axis here somewhere, say, it will be there, and it will give you drop probability there. So as you increase the load, you get increased drop on this axis, and you get increased delay on that axis. And if you increase the curviness, so you put a different algorithm in, so you go to the squared one, you move to the pair of green curves, so it's like a pair of pincers. The more curvy the algorithm is, the higher drop will go up and the lower delay you'll get. And in the extreme, when the curviness would, if you could get it to infinity, you get the sort of thing that Pi and Coddle are trying to do, which is holding delay constant, right? And as you can see, you get a very good intuition here. If you hold delay constant, your drop goes up very hard because TCP has to either have delay or drop in order to push it down. And if it can't have more delay, it pushes up the drop. Is that, am I getting perplexed looks, or do people understand the graph yet? There's a few shakes. Yeah, go on, a show of hands. Who understands the graph? Right, and put up your hand if you're stupid. Okay. Oops, did that move the slide on? No, that was you. Yeah, I haven't finished yet. Currently, in all the experiments that Kuhn is going to talk about in the next talk, we've used a value of 2, so we've done the squared curve, and we did thousands of experiments with that. We're going to move on to 4 and so on, and see, I reckon that will be better, but it's pretty good already. And so essentially what we're saying is you may well get people claiming very good delay results, but if they do, look at the loss as well. And you may well be getting people saying, just as people can give you good delay results and the utilization could be crap, you need to look at all 3 parameters. Yeah? Is it a clarification point, or?
I was going to ask a question. But
yeah?
Not clarification.
All right. Stuart?
Stuart Cheshire, Apple. Very quick point. You keep talking about delay, about loss.
Yep.
And I agree with you. I've come to believe that loss is more harmful than we think. It's very wasteful. But if you do ECN marking instead, doesn't that go away?
Exactly. And the sort of final conclusion is that ECN gets you out of this dilemma. So you can have flat delay, but it's sort of saying, it's an argument for saying ECN and drop shouldn't be considered to be the same thing, because you can't get out of this dilemma with drop, so you need a different algorithm. Yeah.
David Olson. I'm one of the stupid people. What are the units of the x-axis? It
Right.
should be something that's
I was
per second.
I was hoping to avoid that point. The units are dimensionless because L is proportional to n over x, but then there's the MSS in there, and there's the round trip time in there, and you can go and read the paper if you want to find that out. But I thought I'd try and simplify it for this talk by just saying it's a dimensionless number that you can actually. The best way to think of it is that because the more flows you've got in the link, if you double the amount of flows, each will get half the amount of capacity. Yeah, of flow rate, sorry. And so what I've shown here is for the particular normalized load value we've got here, you'll get 1 megabit per second per flow about there. You'll get half a megabit there, 2 there, 4 there. So it's sort of as you double the number of flows, you'll get half the capacity. Yeah.
Bob, you're running out of time.
Okay. So I think we're nearly done. We've just got one more slide, I think. Yeah. So the conclusion, I'll just repeat, is that if you squeeze delay, you'll get more loss. And so really, whatever we do with an AQM, the problem is now, once you have any sort of AQM, your problem is then TCP. Once you've got a reasonable AQM, you can all argue about, oh, my delay is better than his, or my loss is better than his, but actually it's TCP that's, you cannot get out of these dilemmas. And so look very carefully at people's claims, because they're probably just using different points on a surface. And we already know we've got this delay utilization trade-off. And actually, strangely, I'm going to have to say ECN's the solution again. You've not heard me say that one before. The solution to both those problems is that ECN, in the first case, allows you not to worry about what level of drop you've got, because it's marking. And in the second case, it means that you can have lower delay without getting low utilization, because your saw teeth can be smaller and you can have more teeth. So you can, and again, that means you can have more ECN marks, but it does, if you had more drops, you would, it's an impairment, so you don't want that. So I think that is the main set of conclusions. And I guess the other one is that we now have an AQM that allows you to adjust this curviness, so you can trade off delay against loss, whereas I think Pi and Coddle don't give you that choice. They've essentially made the choice for you that you've got to have constant delay, and they've built the whole algorithm around it. So you can't soften that assumption to get less loss if you want it. Matt
Mathis. The thing that you're blaming on TCP is actually a more general problem. Congestion control is an equilibrium process, and for whatever parameters that congestion control is paying attention to, it finds, whatever protocol you're talking about, it trades them off against each other to find an operating point, which is consistent with its algorithm. So if TCP is measuring loss rate, which most TCPs are doing today, it controls loss rate against data rate against queuing delay. And this is true for any variant of any TCP of any throughput maximizing protocol. And this is actually why it turns out the TCP isn't so good for measurement, because this lots of stories about this.
But what Stuart said is still
so.
Yeah.
One of the things that has come to be understood about the old red is actually the smoothing function is broken. Mm-hmm. And I was wondering if you'd actually looked at that, or what smoothing function you used. I mean, the red one in particular is not. The original is not not the right function.
Yeah, I've looked at that for Pi, and I haven't looked at it for my own algorithm, but I've got an idea now why the red one is wrong, and I want to do a better one, and hopefully we can do that in a line as well, because
I believe there was some success with one-way exponential moving average, but I don't actually have the literature on that.
You believe what about the UWM?
One-way moving average. So if the instantaneous is below the average, you pull it down immediately. Yeah. If the instantaneous is above
Which is
the
a bit
average,
like what Kathy and Van did. Yeah.
which is why they did it.
Stuart Cheshire again. I just want to quickly echo that point because that's a very good one. That we fall into this trap of blaming TCP for this and that, when what we really mean is any transport protocol would have to have these properties. Any transport protocol that seeks to find out how much throughput is available by trying, inevitably tries too hard and loses and backs off. So it's hard to imagine a protocol that wouldn't have that same property.
Wait until you've heard Koen's talk. Right?
One question, if I've understood this correctly. I do get the point about ECN. So are you saying that if we don't have ECN, we should rather go for something else than pie and cuddle? For example, my
point at the start is that if you don't have ECN, yes, if you're a perfectionist, you could go for something better than pie and coddle, but don't stop and do nothing until you've done that. You know, it's better to have something than.
So we have something today, it's just not very good. So now we're looking to go for pie and cuddle.
Yeah.
And we have TCP and STP running, so we cannot really change that. Or we can blame it, but we cannot change it.
Yeah.
So, but until we have, of course, the goal is to go for ECN. But as long as we don't have ECN, we should look for something else, perhaps. Than what you've just said.
And the experiments you'll see with the curvy red, we haven't necessarily got it as good as delay as FQ Coddle, but we've got more ability to soften that target and get lower loss as well.
I want to quibble with not very good. Both of those algorithms are 2 orders of magnitude better than drop tail, so do something.
That's what I'm saying, you know.
Yeah. Good.
So pie and cuddle may be better than drop tail, but what you have here may be better until we have ECN. That's what you're saying.
Yeah. You can put it on the table.
Yeah. Okay, good.
So.
I guess I wouldn't mind pie or coddle. I particularly have an objection to FQ, but everyone knows that. And from the experiments we've done, we've found that it scalps off UDP flows, like for your video and things like that, if you've got TCPs in there as well. So, you know, I don't say you should do anything, because I don't particularly like the FQ side of FQ coddle, but otherwise, you want that one?
Yeah, thank you.
Okay.
Yeah.
Thank you, Bob.
Okay. Hello, everybody. My name is Koen de Schepper. This is some work. This is some work that we have done together with Inton, Olga, and Bob. It's in the scope of the FP7 RIDE project, so it's partly funded. I have to say that. So we're showing a proposal for a new AQM. It's called the dual queue coupled AQM. We have a draft, which missed the deadline by a minute, and a paper. So we have a preprint, which is submitted to Connext. So you can find it on the links. So, what we were looking at is, okay, today in the internet, Bob already mentioned, there is this compromise between loss and latency. I mean, queuing delay then mainly, because if you don't have a big queue, you have loss. So this is related to how the drop was introduced in the original, because it was made with drop. So there is a kind of problem with latency with the current TCPs. So we saw also in the data center that there is a big improvement by using data center TCP. So it's used ECN. So we are definitely in favor for ECN, but it uses ECN in a much better way. So it has much more frequent marking because it's a scalable protocol. It means that if the throughput goes higher, it gets the same marking per round trip time, whatever the bottleneck rate is. So it scales up to very high throughputs, while today the current TCP has this square root inside, so it's getting less and less feedback the bigger the throughput is. So with data center TCP, we can in the data center achieve small queues, low latency, and high throughput. So we don't have this compromise. So the question is, can we use it on the internet? Because there are implementations in Windows, FreeBSD, and Linux. Just if you use it today, it's not possible, because if you try to use it, it's only one line in Linux that you can switch on. You get continuously full queues because data center TCP is too aggressive, and high drop rates. So the classic will starve. So we need sorry? Oh yeah, so classic, yeah, maybe I should also explain what we call data center TCP. We see it as a new family of congestion controllers which achieves low loss, low latency, and throughput scalability. So these features are in data center TCP. It's just an example, but other congestion controllers can also have this. So with the classic TCP, like Cubic and Reno, they are designed for loss and take care of that compromise. Data center TCP is designed for ECN and doesn't make that compromise. So you can have all together, let's say. So coming back to how can we have an AQM? So in this dual queue coupled AQM is the first proposal. There are probably many others to have such, first of all, equal steady state throughput. So it arranges that data center TCP and Cubic and Reno gets the same throughput. And the second thing is that it preserves for all this new family for low loss, low latency, and scalability protocols, that they get this low latency that they can achieve, so that it preserves this low latency. So the concepts of, I'm going to show you in 3 steps. First concept is to use a dual queue. And that's necessary because, of course, this L4S traffic TCP kinds family, they can preserve very low latency, so they need another queue to have this low latency, and the other needs a big queue, because otherwise, if it's drop-based, you get a high loss, so, and for throughput, so they need a big queue. So what we do is, currently in our implementation, we do an IP classifier. So in the IP ECN headers, in the IP header, the ECN bits, we use them to classify if they're 0. They go in the classic queue. If they're ECN capable, one of the bits is set, we put them in this low latency because we assume it's an L4S congestion control. So then we use just pure strict priority to schedule, because we want low latency, it must be getting the low latency. So we use a strict priority scheduler, because, and then, of course, like this, it doesn't work. So we need the next step, that is to have a coupling between the 2 queues. And the coupling is based on the queue size, because this queue will be always empty, because it gets strict priority, and this queue will always grow if this one is not empty. So we do a feedback loop from this queue size, the queuing delay. We get in this queue. Sorry? Oh, is there no pointer? Sorry. Okay. Yeah. Oh, yeah. Okay. What's the button? The red one? Oh, yeah. Sorry. This queue size is the classic queue size. So this will grow if there is not enough emptiness in this queue. So, and how is this emptiness created? If this queue grows, the marking probability will grow, and we put more marks in this data center TCP traffic. Of course, we also have to control our own queue, and if we use the same marking probability here to drop, then of course the classic TCP will starve again. So the third thing that we have to add is to make sure that they run with the same speed. And it's a simple rule, how we make data center TCP, for instance, or any scalable protocol which is proportional to 1 over the marking probability. And a classic TCP like Reno and Cubic, they're proportional, the rate, to 1 over the square root of P. So how can we make the rates the same? By inducing a drop, which is a square of the probability, and this square of the probability is undone here with the square root. So the rates with the same P here squared and here not squared will make sure that the rate is the same. So it's a simple thing. We have to think twice here. That's what's called think twice. If, for instance, we agree to make a 10% drop probability, mark probability on data center TCP, we do 10% of 10%, which is only 1% of drop. And if you just apply it like that, so this in fact becomes a kind of curvy reds. This is where the curvy red comes from. We can just make sure that the rate is the same. Is that clear? More or less?
Between the two queues, do you serve them round robin, or does the orange queue only get served when the blue one is totally empty?
Yes. So this is strict priority, means if this queue is not empty, it gets served, and this one gets only served when this one is empty.
Okay.
Because that's good, because if you do round robin, of course, then each class would get the same throughput, and if there are 10 flows in this queue and 1 flow here, this one would get half of the capacity. That's not what we want. By making it strict priority and do the control loop, the coupling, we make sure that if there is 1 flow here and 10 flows here, this one gets the same throughput as those 10. You see? Because they get the same probability, the marking probability, and the one needs a square to undo the square root, and this one just can be applied directly. So it's as simple as that to make data center TCP run with the same rate as TCP, classic Reno. Okay. Yeah, there are some details in our implementation. So in the classic, burst allowance in these things, we introduced the smoothing. It helps. No smoothing at all in here, because it makes it worse. So data center TCP, forget smoothing, not necessary, it makes it worse. A second thing is also that if there is no classic traffic, of course, this queue also needs to be controlled. And we used, for now, just simple step function like data center TCP. Of course, we can further investigate whether other mechanisms are more appropriate. But for now, we just have a shallow threshold of 5 packets, and that's it. Of course, also no smoothing here. It's like data center TCP configuration, min and max threshold the same, and no averaging. So we evaluated this on a real broadband testbed. I did the explanation previous time in ICCRG as well. So we did static or long running flows and compared the throughput fairness. So we went further now. We also did dynamic tests to see whether flow started and stopped. We also got the good performance. And so I'll show you later the results. So that worked also. So and that's why we did the smoothing and so on. We got now some more experience on that. So this testbed, what is it? That are a number of service routers. It's a broadband residential fixed access network where we have service routers, an access node with a real copper line, a residential gateway, a data center TCP server or a PC at home, and a cubic PC at home, which can talk to a data center where there is a data center TCP server and a cubic server. We have in the BNG typically per user shaping. We put it out in a Linux box. We put a shaper of 40 megabits, and we could check with a lot of different AQMs. So I'm going to show you a demonstrator. So I will, with a remote desktop log in into this setup, which is in Antwerp. And we have a GUI, a graphical GUI, which shows the two queues. Well, actually, it's the two classes. This is ECN, the queuing delay experienced by ECN. This is the queuing delay experienced by the drop flows. So after classification. And this is the drop probability, the marking probability shown, some link utilization, and then here we can vary the number of flows. You can see the throughput of the flows, and we can also have some. So these are long flows. So it's a big file copy. These are web browsing traffic, where either 100 requests per second or 10 requests per second. So that's to show what's going on when you start and stop flows. Okay, this will be the GUI, and so I hope this will work out. So I have to turn myself as well. So we capture the traffic at this middle box, this AQM server. And so if we start, so I think now the dual queue is active, we can start a few normal TCP flows. So it's the classic TCP flows, cubic, and it takes a while before the commands are executed. So what we see is we have a curvy red queue, and we have the flows competing with each other. And you see a big variation. If we start some data center TCP flows as well. Yeah, so the scale is here 40 milliseconds. So now, so on average, there will be around 30 milliseconds delay with the curvy red for these 10 flows. These are the data center TCP flows. And this bit here, this pixel, is the queuing delay for the data center TCP. So it's really, because this queue must be 50% of the time empty to support the fair share between those two. And when it's filled, it's only slightly, you see the pixel moving sometimes. So it's below milliseconds now. And it's, the percentage is very low. So no matter how many flows we stop and start, so it takes a while to stop them, and they are restarted, in fact. You see, at the end, the rate is approximately the same. You see data center TCP behaving very well because all the flows are close together, and they stray off and they're wobbling because they get only per X round trip times one drop, and one can stray off very far because by accident he got less drops, while in the other case, data center TCP gets per round trip time 2 marks. So that's how data center TCP works here. If we, for instance, replace the AQM, you see, to start the command by an fqcodl. To see the difference, I've activated fqcodl now. You see that the fair share is perfect in this case. That's because we have a scheduler, round-robin scheduler, per flow. And the flow, as long as the flow identification is okay and there is no collision of queues, it's perfect. But of course, the queuing delay is for classic flows very short. So with a bigger drop, we have here now 1%. But okay, it's between 5 and 10 milliseconds. And the current CODL algorithm cannot hold or keep down the data center TCP. And the queue for data center TCP is much bigger. So I've heard there was another ECN threshold that might be useful to, if it's ECN or data center TCP, that we can have another threshold or another algorithm for fqcodl. So fqcodl can be improved, but of course here we need to know the flow identification with our mechanism. And what we want, of course, is that everybody will migrate to data center TCP. We don't need flow identification. We have a really small queue, and we also have good enough fairness, let's say. Maybe to show if we don't have any flows, Of course, then the queuing delay will be a little bit bigger, but these 5 packets is way different than the 5 milliseconds. And we get here 30% marking, but marking doesn't harm, and we get still a good behavior. Is it an urgent? Yeah.
Just a quick question. Dave Top, bufferbloat.net. You're distinguishing between the 2 queues by the presence or absence of the ECN markings.
Yes.
So if someone were to run a cubic flow the same time as a DC-TCP flow, what happens when they collide in your second queue?
So this assumes that
ECN
can be used as a classifier. But of course, that's another discussion. We might need different mechanisms to identify them. So I know this discussion must be done, but we agree there must be found a solution. So maybe not necessary to do this discussion now. But
okay.
Yeah.
Just check.
But because if it happens, of course, then it will starve. Like it starves. Like I can show you if you use a red queue, then.
No, I was specifically interested in how cubic with ECN competes with DC-TCP with ECN.
So you see here, for instance, this is cubic and data center TCP over a red queue.
Yeah.
And the red queue is really at its step function. So the max threshold is at 70 milliseconds. So cubic drives it to 70 milliseconds. And we get 1 or 2 packets per round trip time for cubic. So it really starves.
So cubic with ECN on.
It's the same. Because here they go in the same queue. If cubic with ECN is enabled, it will be exactly the same.
It will be in the blue queue.
Yes.
You will see DC-TCP with its step reduction versus cubic with its equivalence between drop currently.
Yeah, that's right. There is a little bit different behavior because of the on-off marking. But not sure whether it will be better.
It will probably be starve.
What are you showing us on the screen? So now there is the AQM is red, but of course this tool makes the CDF of all ECN capable traffic. So data center TCP is here the only ECN capable traffic. There is drop applied to this.
Is it 1 or 2 queues?
So this is only a visualization. Here there is 1 queue, but this shows, because now you see the queue sizes are exactly the same. The drop probabilities are exactly the same. The tool only extracts the packets and looks, if it's ECN, it shows it in here. If it's non-ECN, it shows it in there. So even for CODL, if we have 100 or 1,000 queues, it's just a classification. But for our case, these are really the dual queue. These are really the 2 queues because ECN goes in here and non-ECN there. Okay.
I just want to make one point more clear, because you said that everybody who uses ECN has to just use data center TCP, and the point is about that those flows using the service should use a data center like congestion control, which has about the same aggressiveness as data center TCP. It doesn't have to be data center TCP. Yes. It can even be, I think there are solutions to make it simpler, but it has to have about the same aggressiveness.
Yeah, it should be scalable 1 over P. So the rate should be proportional to 1 over P instead of 1 over P squared, because as long as it's 1 over P, the squaring in our algorithm, so between marking and dropping, thinking twice, makes it run with an equal rate. Okay. So whatever congestion control mechanism or algorithm you have in the TCP, as long as it's proportional to 1 over the marking probability, then it will work. Of course, if it has a constant 10 times 10 and data center TCP has 2, then your new protocol will have 5 times more throughput.
My name's Stuart Cheshire. I'm from Apple. I think Dave Tatt was just alluding to something which I talked about on stage at the Apple Developer Conference, and that video is available. But I'm guessing it didn't get a lot of publicity. There was a lot of news about the fact that Apple will be requiring IPv6 for applications, which is kind of not a big surprise because we've been working on v6 for 20 years. The other bit of news that didn't get mentioned is we have turned on ECN with Cubic for all OS X and iOS devices. That's available in the developer seeds that are available to download right now. And of course, until it ships to the public, all decisions can be changed. And right now, the point of having that in the seeds is because we want to do testing. We know that 99% of networks carry ECN traffic just fine. Even if they don't do any marking, at least they don't mangle it. What we're interested in is the other 1%, because 1% of a billion iPhones is still a lot of support calls.
Yeah.
So that's the purpose of having it in the seed for testing. If things are successful, and of course I don't know at this stage whether they will be, but if things are successful by the next IETF meeting, we could have 1 billion iOS devices running ECN on the public internet.
That would be good for ICN, but it might be a pity for this opportunity. So, and will make it more complex to differentiate between the scalable.
I was reporting this news without commentary. I'm surprised not to get any rotten tomatoes thrown at me. But the reason I want to draw attention to it in this room is because this is an experiment at this stage, and the point of the experiment is to get feedback. And we've got precious little feedback so far, which I think is lack of awareness of this, which to me is much bigger news than V6. So please spread the word. If you haven't done it yourself, download the seed and give it a try, and let's find out whether this experiment is successful or not.
Yeah. Be brief.
Well, Bob Briscoe, we're very much aware of Apple's or your announcement at Developer Conference, and the idea is that we would need some identifier to identify the L4S traffic separately from the classic traffic. We were thinking it could just be ECN, but once you announce that, we're going to have to do it either on ECT1 or we're going to have to do it on ECN plus diffserv code point, but we want to make sure that we don't burn a code point just for the period while Apple catches up and does this. So I think maybe a diffserv code point might be best, because then that can just be done locally for a short while and then goes away and we can just use ECN in the future. But yeah, that's a separate debate.
Maybe quickly one remark about data center TCP as it is now. The data center TCP as it is now is not really safe because it doesn't respond to drop like it should be, like Reno. So there are some migration things. So it can be used, this lesser safer data center TCP, let's say, in coexistence in data centers, so in controlled environments, or in walled garden deployments like we proposed its data center to the home. But for public internet use, I want to say, fall back to Reno or cubic behavior on loss is important, of course, because there is a lot of network equipment not only doing drop. ECN is a less problem because there is not much ECN mechanism routers in the network now. But if there are ECN enabled routers and devices, then detection of these classic ECN routers is important. ECN negotiation issues is something that should be resolved, and handle a window of less than 2 when the round trip time is very low, because we are here working with 0 queuing delay. It means that it's also important that if the window goes below 2, and now there is a minimum window of 2, so there are always 2 packets in flight. If it's 100% marked, it cannot go less. And that's a talk Bob is going to give also in TCPM, I think, ICCRG. Yeah. And then also we have to look what data center TCP, the current implementation, is doing when the round trip times become longer. Okay? Just, I think.
Quick comments.
Hi, David Skenazy, Apple. I wanted to ask, so about the public internet use. There's kind of a big issue between how DC-TCP interacts with regular TCP. Like, one of the nice things about ECN that we're testing right now is that we can just turn it on, and most networks, it just works. And that way we say, all right, we turn this on, then we can go to the network operators and say, guys, now you have an incentive to enable AQM and ECN marking because a lot of your customers have devices that support them. And they can go up to the management and say, we should put resources into this. There's a motivation, whereas right now they don't have as much. For this, it sounds like you don't have or at least I'm not seeing an as easy way to have an incremental rollout, because as soon as you put TCP on the wire, it just wrecks everything else that's there. So are you, I could be missing out, but of saying that, or you send it out and then you fall back?
The data center TCP as it is now, there are some easy fixes that can be done. And then, of course, it will need equipment in the network that supports this square. But since it's a very simple thing, it can maybe be implemented, maybe even in existing hardware, don't know. Yeah, the other problem is, of course, if we are now enabling ECN at this stage, it will make it harder also to migrate or distinguish the scalable transport protocols, which make a perfect use of ECN. So they're developed to use ECN. Now we are going to deploy with ECN the old-fashioned congestion control schemes. So it's a little bit of it. But I think it's a discussion.
I would like this discussion to continue, but please on list. We are unfortunately almost out of time. But I would like to have Wolfram's talk still presented here, and please continue this discussion on the mailing list. Sorry, Dave.
Okay, ladies and gentlemen, my talk is about global synchronization protection. Global synchronization happens whenever you have several TCP flows sharing a common bottleneck. Then the flows typically do their congestion window reduction all at the same time, or at least half of the flows do it at the same time. And this causes large queue oscillations and large delay jitter. The protection scheme is just to avoid this kind of synchronization. It is very simple. It sets a threshold on the queue, and the threshold can be in delay or in size of the queue. And if the threshold is violated, it drops one packet. And then it sets a no-drop interval where it does not take into account anymore the threshold. And it waits until the round trip of this one drop causes a congestion window reduction so that the queue drops below the threshold. The algorithm is surprisingly simple. It's just two questions. Are we above or below the threshold? And the second question is the expiry of the no-drop interval in the future or in the past? If you answer both questions with yes, you drop the packet, which is at enqueuing almost do nothing, and then you set a new expiry value. It's just a value, it's not the timer also, and so there's also no randomness or something else. Next slide. Here we have an experiment, how it works in a real Ethernet test bed. So we have a growing queue, and whenever the queue reaches for the first time the threshold, it drops one packet, and then the queue grows a little bit further before the reduction manifests itself in the queue size, and then it starts again growing and drops again. So this is the so-called single drop operation of this algorithm. But well, we can have more aggressive traffic than we expected. We can have, for example, more flows in the traffic. We can have much shorter round trip times than we expected, or we can have more aggressive traffic, or like cubic, for example, and we can have partially unresponsive traffic. And that's why we need to adapt the no-drop interval. The adaptation criterion is quite simple. If we are more times above the threshold than below, then we obviously need to make a shorter interval. And with the shorter interval, we finally end up in a kind of periodic dropping, because we many times have the expiry of the no drop interval, so that we get a kind of a bang-bang controller. If you're above the threshold, we drop periodically. If you are below the threshold, we do not drop any at all. No. From a control theory point of view, it is the basic control loop, which is these three statements that I showed initially. It is quite stable and robust, and outside of this control loop, we have an adaptation loop that integrates over the times above and below the threshold and adjusts the intervals accordingly. So the basic loop keeps the TCP stable, and the control loop is outside of this basic loop, so that we can do here some heuristics and whatever we can do, time constants that are independent of the TCP itself, and so on and so on. Here are some results. What we did here is the cumulative probability distribution function of the different AQMs, and the probability distribution function for best operation should start at 0, meaning that we do never have an empty queue. That means we have full link utilization, and the curve should reach 1 as steeply as possible to have short queuing times. And it is obvious that with more flows, we get a gain over tail drop. So this is a little bit something different than Bob explained right now. So we have to discuss this, I think. What is the surprising here is that we see with this global synchronization protection, we see almost the same effect as with Chordal and Pi. And also for larger numbers of flows, it's always the same gain compared to tail drop. And the most surprising thing is that we do not have any gain compared to tail drop with a single flow. For GSP, this is obvious because with a single flow, we cannot have synchronization and we cannot remove any synchronization. But Chordal does it the same way as tail drop, and Pi spreads the queue even more larger, so Pi does not reach here the 0, so Pi underutilizes the queue, this is the link here, and it spreads the queue even worse than tail drop. Next slide. One test that we did a lot of tests with unsteady traffic conditions, with traffic stalls, changing with different round trip times, with changing number of flows, and so on and so on. So even with changing train rate of the queue. Here's one experiment where we added UDP traffic, unresponsive UDP traffic. So we had 100 megabit TCP traffic and injected into that link additional 90 megabit per second UDP, unresponsive UDP traffic. It's clear that all AQMs at the first moment saturate the queue because there are too many packets in flight. But then they remove this problem, so Pi is the fastest here. Chordal and GSP do it after a while, and then they stabilize again in the range where the threshold was set. And here again, GSP is quite stable because of this inner control loop. Even if it drops, it drops 10 times, or 9 out of 10 drops are lost. And still it stabilizes the traffic at the threshold. So we had a lot of other results here, but the time is over, I guess.
Unfortunately, yes. So we are already over time by 10 minutes.
I have only one slide for a conclusion, if you can show it. Yes. So what I wanted to say is global synchronization protection, even if it is only intended to remove the global synchronization, it does essentially the same as the other AQMs. No other AQM is doing anything better in that case. And GSP is a minimalistic solution, so it's just 3 statements. And we have a draft on this here. And we have a paper that was recently published at HBSR in Budapest.
And I believe you have sent a link to this paper on the list, or will send.
The problem is that it's not published. It's going to the IEEE Explorer, but there it is still not. So please ask me. So send me an email, and I can give you a personal copy or whatever. But it's not public yet on the internet.
So I would like to encourage some discussion around this algorithm on the list. Some feedback, especially from hardware vendors, may be interesting because this sounds like an AQM algorithm that is best suited for core network links rather than the other algorithms that we have discussed so far, which are more suited for edge, the edges of the network. With this, I think I conclude today's meeting. Thank you very much for hanging out here for 10 minutes longer than we've had. So one last minute, Bob, please.
I just wanted to say that
you've been running 10 minutes over time already.
Yeah. Just wanted to say that we designed ours for core, and it was for a BRAS, so it was also designed to be very low.
Okay. Good. Thank you very much.